welcome to our next lecture, lecture number 9. So we are coming closer and closer to the end of the course, and today we are going to speak about propagating spin wave spectroscopy. This will be still a part of lecture devoted kind of the last methodology, which is used intensively in magnonics, very powerful technique. Very briefly we'll discuss it, and then we will switch to magnonic crystals. In magnonic crystals, this is already more scientific results, more in-depth, but here I made a selection of that effects which I believe are of interest for you to understand how actually to work with spin waves, what kind of interesting phenomena can be observed, how to deal with them. And so let's start with PSWS. What's the idea of this technology? Principally, it's very simple. You have a spin wave waveguide. Here, for example, shown yttrium iron garnet placed on GGG substrate, and you have one antenna to excite spin wave, and you have another antenna to detect spin wave, you just measure transmission from one antenna to another as a function of frequency and for different magnetic fields, and you will get all information principally more or less about spin waves which you need to know. And how this antenna works. So input microwave signal is applied here. It's very simple. It's the same as in ferromagnetic resonance studies. So we will use the alternating field around the antenna. So if you have antenna with a current, here's the cross section. Current is changed in one another direction, and it creates a field in one another direction. And in such a way, you will excite magnetization precession, like it was shown in the animations at the very beginning. The difference from ferromagnetic resonance approach is that this antenna is usually very narrow, since the width of antenna defines the smallest wavelengths which you can excite. Yeah, so if you work with ferromagnetic resonance, the ideal case is to have a very broad antenna when all your sample will be placed in the same uniform applied magnetic field, RF field. And when you want to work with propagating spin waves, like in this case, you're trying to make this antenna as narrow as possible in order to to apply this field locally, that you can excite short wavelengths, which then propagates through the spin wave waveguide. And of course, we shouldn't forget about bias in magnetic field, which can be applied in different orientations along the spin wave waveguide, perpendicular or transverse. Yeah, so here's one of the very old structures. I made a photo somewhere in Kaiserslautern. So here's this antenna, how it usually looks like. This is a 50 ohm characteristic impedance microstrip line, so it's metallized at the bottom. This material looks a bit transparent, so it could be aluminum oxide, alumina, or could be principally, pretty often people use simple duroid for microstrip lines. Then you have 50 ohm matched line, and here it was soldered to this coaxial line, which is 50 ohm matched. Nowadays we use pretty often so-called end-lunge connectors, which where you clamp mechanically, also works quite good. And large connectors, they are magnetic, non-magnetic, depending what you need. And the antenna itself is staying here, and it's very narrow. So usually we're going for something like 50 micron wide, sometimes 25 micron. And here you see that it goes just, you probably hardly can see it, but here it's just such a narrow antenna between these two parts. There is no adapter. But nowadays what we do, we use an adapter, because this 50 micron wide antenna, if you use microstrip line, it cannot keep 50 ohm characteristic impedance, yeah? Because it's not CPV, it's microstrip line, and when you make it very narrow, characteristic impedance will be different. Therefore, what we do nowadays, we narrow down this part of microstrip line simply to make a wave number characteristic impedance conversion from 50 ohm to some characteristic impedance of the antenna. What's also very important here is that on the other side it should be shortcutted. So there are two ways how people are doing shortcut. It's either mechanical, real shortcut via, yes. So just go such a tube down to ground. Another way to go is to use such a big area like it's shown here. It's more or less capacitor, which is working as a shortcut for microwave signal. Principally, both works good. Maybe for lower frequencies capacitor, you will see that it starts working worse. Yeah, so here we have one antenna. On another side, we have another antenna. So we excite spin wave here. We detect it on another side. Here you see such metal constructions and even some additional metal, which is indium. Most likely, it's a very soft metal. This is done for different kind of microwave tuning. So that's how micro engineers are working. If you need, for example, to tune this antenna that it works especially good at some given frequency, you could try to get some kind of resonator. So there are some different tricks how you could optimize the antenna for your structure. But general idea is that you send it from one to another. So this is our yttrium iron garnet film. Yeah, it's cut under some angle, 30 degree usually. The reason is very simple: to avoid reflection. Spin waves propagate, it reflects, it scatters into higher K modes, dipolar exchange spin waves with zero frequency, with zero velocities, and more or less all energy is absorbed at these edges. Doesn't reflect. There are other ways how to make absorbers. And this in the middle, you see it's so-called open dielectric resonator. So particularly this setup was used for parallel parametric pumping experiments, which is a bit other physics, but we are not going in there, but that's just a resonator which helps you to concentrate electromagnetic field in this region. Good, but our idea, yeah, to send signal here and to detect it on another side. Therefore, we have input and output antenna, like it's shown. So when you have input and output antenna, you send such signal. For example, you apply magnetic field along the strip, so you work in the backward volume magnetostatic geometry. Then you will see it's just connected to vector network analyzer, and you measure transmission as 2-1, so transmission from port 1 to port 2 as a function of frequency for given magnetic field. So here it was around 180 millitesla. And to understand this curve, you just need to turn this dispersion and place this transmission and place your dispersion characteristic next to it. So what you will see is that here, for the frequencies above backward volume spectrum, where we have no spin waves in this range of K, we still have some signal, but very small, minus 50 dB. So minus 50 dB, it means the transmission 10 to the power minus 5 from one to another. So it's very small power. It's transmitted, but still there is something. It can be simply noise, thermal noise, but more probably it will be electromagnetic leakage from one antenna to another. So it means that the signal goes through YIG, so you excite spin wave, it propagates, and then in the same way, field created by spin wave is always, as evanescent wave goes outside of the sample, and when second antenna is placed in this field of a spin wave, it will induce electromagnetic signal and you detect it. It's from the second antenna. And outside of the spectrum, you cannot excite spin wave, but still there is some electromagnetic signal which goes directly from one antenna to another, and you can induce magnetic signal here simply by as a leakage. And yeah, and that's exactly what we see here, this minus 50 dB on the right side or on the left side. So then when we go to lower frequencies, we see that there is a good transmission, and good means in this case minus 20 dB. So this number changes, but it means that only minus 20 means 10 to the power minus 2 in a power ratio. It means that only 1% of our signal is able to pass from one antenna to another. This is kind of standard typical value. If you take, for example, distance between antennas 1 centimeter and the thickness of YIG is 6 micron, for example, without any optimization, not very good antenna and so on. So where do we lose 99% of energy? First of all, 50% is lost already by this antenna because it excites 50% here, 50% there. Second, you have damping. So when spin wave has to propagate 1 centimeter, there will be decay. So the larger the alpha in your system, the larger will be the losses, the smaller this value will be. Second, group velocity is very important. Yeah, so if you take sigma eq, this velocity, this value will go up. So it means the sigma is eq as a faster spin waves. You can decrease losses due to damping. And next, what we need to, of course, to take into account is excitation and detection efficiency of antenna. So it means that if you have here antenna, you lose some energy, so only part of electromagnetic energy is converted into spin wave. And if you detect only part of it. So all these factors together, when you multiply all of them, or in dB scale, you add all of them, add up all of them, you will get this minus 20 dB losses. What's going on then? If you decrease frequency, you see the transmission decreases, and the reason is that the antenna cannot excite very large wavelengths. Yeah, so in the simple, very large K, very small wavelengths. So in the very simplest case, you can see it like this. If this is your size of antenna, and you assume that field is localized to antenna. Yeah, of course, it's not physical, but it works in the simplest case. Then you can excite wave of this type. Yeah, because so when width of antenna is approximately half wavelength, because this signal has one phase and at this point it has opposite phase if you frozen time, yeah, wave is running. And you can excite very big wavelengths. It's like when you take a guitar and you with a small finger you can excite big mode. There's no problem to excite large wavelengths, but you cannot excite small wavelengths. Because when you're trying to excite small wavelengths, the same field, which is uniform, you're trying to excite simultaneously this part of magnetizations which are in antiphase. Therefore, the reason for that, for the slope, is that we decrease magnetization like it's shown. We decrease the excitation efficiency like it's shown here. And it means that the smaller the frequency, the higher the K, and the less efficient our antenna excites higher K. Good. Yeah, so here is another antenna, also microstrip antenna. So here you see some little adapter. So here is again capacitor to shortcut it. Why we need shortcut? Because if you have antenna, what happens here, so this is a microstrip antenna. What happens here is you will anyway have some reflection or standing wave. But if you have here shortcut, then what happens here, you will have a maximum of current. So if this is density of current, you will have maximal density of current at the place of shortcut. And if you have higher density of current at the place of shortcut, it means that field will be largest. If you will put it open, you will still have a standing wave, but here will be a zero current. And zero current means that the antenna at the end will be working quite bad. And of course, this is, I draw it here, not spin wave, so it's electromagnetic wave, which has centimeter long. So yeah, so principally it can be as long as all the structure. But still keep in mind that what's going on here at the end is important. So in this particular case, there are 3 antennas, so you can do it with 2 or 3. So third was done simply as a gold wire, probably 50 micron bite. Still works good. All is placed underneath the sample. And here we work in backward volume geometry. And here I show you the anime video from its experiment from brilliant light scattering spectroscopy. So I told you that BLS has time and space resolution. Therefore, you can make such nice videos when spin waves are excited in the form of pulse and propagate in both directions. And you see that system is quite symmetric. So antenna excites in one and another direction with the same efficiency. Yeah, and as we discussed, the distribution of this mode, magnetization precession, intensity will be cosine across the thickness. So this is the thickness of our waveguide. Now, if we go to the Emanetzhov mode to magnetostatic surface spin wave, when field is applied perpendicular, all the same. But when we apply a microwave pulse, you see that it excites only in the one direction. And as we discussed last time, it's not because of the distribution of this one, but it has something to do with the antenna itself, with the way how antenna is excited. So we discussed it in the previous lecture. Yeah, but there is a distribution exists here, but it's quite uniform in this particular case. Coming back to antenna, so if you have such cross-section of antenna, then first what you need to do, you need to calculate a distribution of field. So you will have some field created by antenna, X component, Y component, like shown here, so X, Y. And principally you can find analytical formula, so in this thesis you can find it, is given this formula. If you want to have more precise calculations, then probably some tool like COMSOL multiphysics would give you a good example, but the idea is that we need first of all to calculate magnetic field, which will show as some, if you can see these arrows, but they are pointing like I move my pointer, so it's more or less Ørsted field around, but of course will be not exactly the same if it would be infinitely thin wire. Having this distribution, Hx here is shown with black, you see that its distribution behaves like this, symmetric. And Hz in that direction is antisymmetric. So also keep in mind that even simple microstrip antenna, if you use this component to excite spin waves, there will be a component will have one sign, and here it will be the opposite sign, pointing like this. Therefore, it will be antisymmetric. But what you do afterwards, you just take Fourier transformation from this field as a function of coordinate, and this will give you immediately the excitation efficiency. So that's what I have drawn here in very kind of finger-like model. You can do it properly if you will have distribution of fields, and you decide which component will work for excitation for you, or you use both, and you do Fourier transformation and you will get such behavior. And decrease for simple single strip line. If you will use so-called U-shaped antenna, like half of CPV, when you have current flowing in one direction and then it's coming back to the opposite direction, the distribution of field will be different, and you see that also excitation in K will be different. And please pay attention to the fact that all these more complicated antennas, U-shape, CPV or meander, they do not excite K equals 0. At least they should not. They always have excitation efficiency for some given K. Therefore, keep in mind that you need to work which wave number is excited by your antenna. And this one, if you want to have a possibility to work in a broad range of wave numbers, then you use just a strip line antenna as narrow as possible. Then you have possibility to excite spin wave in a broad band. And which exactly K you excite is simply given by the frequency. So you define frequency and simply due to dispersion relation, so you just by frequency define which K is excited if you work CPU. Is this clear? Oh, good. Good. Yeah, so here is just continuation of the same story. This is coplanar waveguide. Again, one current flows here, two others here. It's like that. Similar to U-shape, maybe this peak is a bit more narrower. And there is also meander type antenna. Meander when it goes like this. There are different designs I do not discuss, because when you make this antenna, you also still have to think about characteristic impedance, how to send microwave signals that it goes through the structure. Therefore, pretty often people put such ground here. Additionally, or people take this CPV, which is 50 ohm matched, and then all three wires bend in order to have like 50 ohm matched, but meander. And in this case, you see, if you have 4 periods, you will have such a narrower peak. If you have 10 periods, You also the wavelength which is excited is given more or less by this antenna. So distance between two points where current is the same will give you wavelengths, and it means that it works as a good, very efficient excitation for the one concrete key and for one wavelength, and then the more periods you have, the narrower it will be. You are coming closer and closer to a delta function. Also pay attention that there is this electromagnetic leakage here between antennas, and in order to minimize, of course, these guys will have small electromagnetic leakage because field created by this antenna at some distance will be compensated by the field created by the near antenna. Therefore, CP meander is a good idea to decrease electromagnetic leakage. In general, all this, when you think about antennas, it's all about simply Fourier transformation. In the same way, like we go from t time space into frequency space, we just do Fourier transformation and we can move from time to omega or from omega to time. Exactly the same is going on in the excitation. When we discuss excitation of antenna, you have distribution of field as a function of coordinate. You do Fourier transformation account to the distribution. Excitation efficiency is a function of k, and vice versa. So all is quite straightforward. Just keep in mind all the simplest formulas for Fourier spectrum. Yeah, so this is, if you have rectangular antenna, then you should expect something like sinc function. If you have, this is closer to meander, yeah, when you have periodic excitations, then expect something like delta function. It means that only given k will be excited. If you manage to create an antenna with triangular distribution of field, you'll have something like this. Good. So much about antenna, how it works, what you should keep in mind. Maybe before I will switch to the next point, please keep in mind, I did not discuss here propagating spin wave spectroscopy for nanostructures. Because here what is shown is macro structure and signals are very big. So YIG is thick, absorption is strong, you excite good spin wave, strong signal is detected. Therefore, this what is shown here is just direct signal as it is. You connect VNA, vector network analyzer, and you see it. If you do propagated spin wave spectroscopy at the nanoscale, and by the way, these antennas usually they are different. So you separately fabricate antenna on top of your something like this, like it was shown, yeah, and then you just put your YIG sample on top. Sometimes glue in 4 points, and special glue which is transparent for microwave, of course. And when you do the same at the nanoscale, then it usually works different. You do not have this flip structure, but you deposit antennas directly on yttrium iron garnet. Antennas then, of course, are smaller. Usually people work with CPVs also in order to keep 50 ohm matched. Something like this. Distance between antennas then will be, for example, 10 micron or 10th micron for yttrium iron garnet. And what's important then that the signal which you detect is actually not as pronounced as you would like it to be, and oops, sorry. Give me a second, I will find again the same slide. So here you see quite strong signal from minus 20 dB to minus 50 dB. If you will do the same at the nanoscale, the signal might be in the range of 0.1 dB. And then signal is very small, it's you hardly can see it in the noise. Therefore what people do, they always show the signal subtracted minus reference or divided by reference. So principally what you do, if you have such signal, then you perform another measurement when your field is different. So when you shift spectrum here or here, or sometimes people simply apply zero field or very large field, but we usually trying to slightly detune it. And then you will have here only electromagnetic leakage with taking into account cables, reflections in antennas, and all these troubles, microwave business, which has nothing to do with spin waves. And then you can subtract that reference. Therefore, usually you see slightly different pictures at the nanoscale because it's abstracted. Also check papers how to do it properly. There are many papers Michael Urbanek. So there are many experts on propagating spin wave spectroscopy at the nanoscale, but you need to be careful how you subtract it. Yeah. I think quite good result gives the same approach like we discussed in the ferromagnetic resonance story. Calorical, yes, she has some in that paper about FMR. She shows a formula how to do subtraction of reference signal. The same approach can be used here. Good. So much about nanoscale, and now imagine that you work not with a waveguide but with a plain film, so there is no structure. And in reality, it's much more complicated. So waveguide, why it's comfortable to work with waveguide, that as soon as you have excited spin wave here, it doesn't matter which mode it has, which property, which group velocity, and so on, because spin wave is usually complex. It can have different group velocities in different directions. There is so-called acoustic phenomena and so on, when it propagates from point source not along all directions, but in the form of some beam. But as long as you have waveguide, it always runs along. And everything in your life is easy, and also it's easy to put antenna, because you put antenna, it doesn't matter how you brought your signal, how you should make the shortcut. But if you have a plain film unstructured, then it's getting, and you want to excite a beam in one point, then it's getting complicated, because when you will bring here microwave current, most likely you will excite spin wave everywhere in your path and afterwards also. Therefore, people are thinking how to create a point source excitation in one point. And this idea from the group of Maciej Krawczyk from Poznań, and what they did, they again use the same approach of Fourier transformation and so on. And they use CPV, it's numerics, CPV, when they of one width and one sizes, and here they narrowed it down in this point. And let us see on the Fourier transformation of the narrow part. When it's narrower than spectra in Fourier space, it will be broader. So this is Fourier transformation of the CPV here. And this blue one, it's a Fourier transformation of the field in this big class region. And then what you do, you just select the proper K simply by tuning frequency. You tune frequency in order to work particularly with this K, and you see you can find such a point when you are not allowed to excite anything here in the big part of waveguide, and you excite it only in the narrower part. Then when you send such a signal through through the structure, what you will get excitation of such a beam. It's not laser, it still will become broader and so on, there will be distortion, but anyway you have a nice point source excitation. Yeah, so we also did a bit played with it around at the macro scale, so you can do principally the same with, not with CPV, but microstrip line. You can narrow it down here. You again can find such points that you excited good at the narrowing down point and not in the wider waveguide. And here is result of MUMAX simulation at the macro scale, how CPV works to excite such a beam and how microstrip antenna works to excite such a beam. Always pay attention to edges, so when you want to do experiment, edges of your sample still will be an issue. One more technique to detect. I worked with it only once as a group of Carl Patton in Colorado State University in the US when I was short-term intern there. And this is more or less the same propagating spin wave spectroscopy, but it gives you a possibility to do time resolution you have always, but also gives the possibility to do spatial resolution. So what you do instead of second antenna, which is constant, and then you measure only at one position and you measure everything across the waveguide width, but you can create such a small loop. For example, this was just on Andrii, a macro structure, but you can do it in any different ways. And then what you do, you just change position of this loop on your waveguide. And then you can get 2D map like it works for BLS by simply measuring in different positions and saving time-resolved pictures. Then when you put everything together, you again will get movie like for BLS. But of course, this one will measure only coherent waves. It has much worse resolution in space, and but it has much higher resolution in frequency, for example. Therefore, it's also interesting technique. Yeah, so here's one movie. It was 2004, so I was writing software to make scanning and to process data. And this is just some working file I just found somewhere in my archives with OpenGL libraries. I remember I managed to connect OpenGL libraries to Delphi script. And this is how wave looks like when you work with this inductive magnetic probe technique. So you see what's also the advantage compared to BLS is that you see phase, like it's shown here. Yeah, just one more technique, but not very commonly used, but just keep in mind that this is probably the simplest technique and it has many advantages. And I'm ready now to come to the magnonic crystal part. Other questions about propagating spin-wave spectroscopy? Everything was very easy and clear. Good. Andrii, yes, Rusty?
Yes. What is the excitation efficiency of macroscopic waveguide in this cosine excitation, like cosine waveform over the width of the waveguide? Like.
So you mean now excitation efficiency of this?
The antenna, yes, because like it's not a homogeneous form, but like this cosine. What is the excitation efficiency of the antenna about this one, and about the higher modes that could exist in such a waveguide?
Yeah, so usually higher width mode, higher thickness modes we don't really see here, or we see them but in the form of interference. So it might be that in this peak, in the signal which you measure, that there is interference. So usually we see here these guys are associated with a higher width mode, yeah, because if you have higher width mode, dispersion goes from higher frequencies, and then you pretty often see here some more peaks which are associated with higher width mode. If it's about thickness mode, then it's getting a bit. More complex. So we principally excitation efficiency will definitely drop down. Maybe that's the reason why we don't see them so pronouncedly. Because if you have thickness, and if you want to get the highest excitation efficiency, you probably would need to have unpinned case. So it means that your mode will be uniform. Then when you put it in the uniform magnetic field, exciting field, it will be the highest. So if you have pinned case and you have this, excitation efficiency will drop because kind of area drop down, but it will be still okay. I will come back to the question about number. If you have second mode, it doesn't work at all as we discussed. Yeah, but if you will have a third mode, then this two, this and this one will be in antiphase. They will compensate each other, and you will still have some small fraction for excitation. So excitation efficiency will drop. It will be 1/3 of this one. If you go to the fifth mode, it will be 1/5 of this one. So it decreases. The higher the order of mode, the smaller is the excitation efficiency, simply because you always have to check that this is plus, this is minus, and they are compensating. Now coming back to the question of excitation efficiency. So as we discussed, here we have 20 dB, so let's say 99% is lost. Where it comes from. So in the simplest case, you can split it into two contributions. Let's say you can say that 10 dB are lost for the spin wave damping, and 10 dB are lost to excite and to detect. In the roughly. Of course, you need to take into account that it excites in both directions. So principally, it's 3 dB less. So 50% means 3 dB. Therefore, if your antenna would excite only in one direction, then this one would be 70 dB. And then 17 dB, split it into two. And then it means that you will have 9 dB, which is lost, roughly 9 dB, which is lost to excite and to detect spin waves. And then you just divide it, divide by 2, so it means 6 dB. 6 dB will be our excitation efficiency for one antenna. So 6 dB is 4 times. So it means that excitation efficiency of this antenna, around 25% of energy goes into spin wave energy, and 75 not. This is very rough estimation, yeah, from simply based on this value. But as I said, there are papers where people try to build microwave filters. They have 2.5 dB here. So it means that to excite, to detect, and dampen, you lose 2.5 dB, which is alright. So then excitation efficiency will be very high.
Then a short follow-up question. In these waveguides, microscopic ones that you showed, like the antennas are always like somewhere in the middle of the sample, and the edges are cut down to 30 degrees.
Yes.
If you would put the antennas directly on the edges of such samples, like without cuts, but just on the edge or even a bit off the edge where it's not touching the sample, would then the efficiency of the rested field like excite everything only in one direction and it would be more efficient? Or would it still be?
Yeah, so question of Rostislav is if we can improve excitation efficiency if instead of having this absorber, we will put a 90-degree cut, yeah, and kind of mirror. Yes, it should. Actually, always wanted to try it, but never did yet. But we will, because if you will go to surface acoustic wave, okay, they have these antennas, like finger-like antennas, and because you need to apply electric field here, and then they also the surface acoustic wave. It's very good, high efficiency of excitation. That's why we have each our smartphone has tens of such filters, and this antenna excites usually with efficiency minus 3 dB because 50% goes there and 50% goes here. But what they did in order to avoid it, they placed here break mirrors. So from the same metal, they just put such array of stripes, and then everything what is excited in this direction is reflected and goes on in phase. Therefore, they have a transmission from one input to output, less than 1 dB. They're really cool. And in our case, this also would be the way to go. The only point, you can still do magnonic crystal. That's exactly what we try to, we'll start talking about it, because this is nothing else as acoustic phononic crystal. And we'll discuss now about magnonic crystal, but the easiest point would be, of course, just to cut it. Because advantage of spin wave compared to surface acoustic wave is that acoustic wave propagates in substrate everywhere, so you need to find a way how to localize it within your sample. And spin waves, it's easy because it never goes out of magnetic media. Therefore, if you will make this cut here, 90 degree of high quality, quality is important, because if it will be rough, then you will excite here higher order, high K dipolar exchange spin waves. But if cut is proper, it's like mirror, then you can get such situations that this wave and this wave are in phase. Of course, what you need to do carefully here is to define this delta properly. That because if you will make delta not correct, then they will be an antiphase. They will compensate. But if you will choose the delta properly, then theoretically you should be able to enhance excitation efficiency.
And if you would put the antenna directly on the edge?
So there are many works when people, Volodymyr Kruglyak is investigating it. I forgot. He names this phenomena as the edge. So the question is if to put antenna directly here at the edge. The point is that when you have coordinate and internal field of your antenna, and if you magnetize it in backward volume geometry, then here will be non-uniform field. This is end of your antenna. And when you will place antenna in this non-uniform field, it's question what's going on here. But principally, it was shown it's in all times in cylinders or big bulks that people can use this non-uniform field, or Volodymyr Kruglyak is using it as a nanoscale, because in this case, principally, you don't need antenna. What you can do, when you have such sample and you will put it into the uniform field, that everything is irradiated everywhere with the same phase, then principally this region, non-uniform region, will act as an antenna on its own, and it will excite spinoid. So principally any non-uniformity you have in the sample, just some hole and dot, antidot, or whatever, just irradiate it with microfilter, and it should work as a micro source, as a spin wave source. Therefore, and coming back to your question, if to put antenna here might be better, might be not. So this is a topic of investigation. We never did it. Good. Thank you. Good. Then let's move towards magnonic crystals. So here I made a selection of that papers which I did myself. I did habilitation in magnonic crystals. But as I said, the main idea is to show you some fun experiments and which should give you better understanding about spin wave business. So I will speak only about 1D magnonic crystals, so one-dimensional, but in literature you will find many two-dimensional and three-dimensional theoretical magnonic crystals, but we go only the simplest case. What is magnonic crystal? It's a media which is periodical, magnetic media which is periodically in space. So it comes from analog of photonic crystal, and photonic crystal comes analog from a real crystal. So as there were real crystals, Breck has found that if you radiate it with X-rays, you will have maxima minima. So Breck scattering phenomena, and people moved the same idea to photonic crystals, but periodicity now it's not atomic scale, but it's on the scale of wavelengths of your light. And then the same idea moved to magnetism in terms of magnonic crystal, where again you just take any media and you change your properties periodically with the lattice constant A. So it's analog to photonic or sonic crystal. Sonic crystals, that's phononic crystal, which I have shown, which is used in our devices. Why magnonic crystals are interesting? Because you create artificially the structure. So it means that you can engineer new type of material where properties are given not by the nature but by a human being. Yeah, so I just want to design such material with such a properties which has a band gap is here. Yeah, of a photonic crystal, I want to have colors that it passes all frequencies except one frequency, and except one color is able to pass through. So medium. So you design it on your own, and that's the main idea behind it. So Breck scattering phenomena, you all remember it. The easiest case is to rewrite Breck law in the simplest way when incident angle is 0 degrees. So it means that simplest possible situation. And here are array of our reflectors where spin wave will be reflected with a periodicity A. And what we need to keep in mind is that reflection efficiency from each of these reflectors is usually very small. So it varies from less than 1%. Some cases when damping is large, you want to keep it closer to 10%, but principally reflection efficiency should be very small. So it means that in general, wave should propagate. And then only small fraction will be reflected here. And then small fraction will be here reflected and small fraction will be here. And then it's all a question, what is the ratio between the periodicity and the wavelength? If you will create such conditions that wave which propagates two periods, so runs between one reflector to other and back, accumulates a full phase, 2 pi phase, so it means that lambda is equal to A, then you will have a resonance condition for reflections. And if all these reflected waves from each of them are in phase, then you will have resonance condition for reflection and everything will be reflected back. Nothing goes through, so this one behaves, it will be actually classical Bragg mirror, and it works as it's principally Bragg mirror I use nowadays in lasers, and they are better than real mirrors. But it's sufficient to change wavelengths or periodicity when this resonance condition is not satisfied, and then everything goes through the structure, through these periods without practical reflection, and you can have kind of mirror behavior. So you can switch for one frequency, for one wavelength, it works as a mirror, for others it works as a glass. To speak about the same in terms of dispersion curves, so here is simplified dispersion curves for backward volume geometry, so you see it goes down for spin wave propagating in one direction, for spin wave propagating in the opposite direction. It's simplified to simply line. Yeah, we remember that it's not line, it has such band, but in some frequency range it can be considered as a line, and that's what we show here. And in the absence of Bragg scattering, it behaves like it's this. But as soon as you have band gaps at particular k pi over a, so this is more or less the first band gap when n equal 1, then it means that you have two special cases, that it's pi over a, and here's minus pi over a. So it means that particularly for these two wave numbers, there will be Bragg scattering working. And it means that then in the dispersion of spin waves, there will be formation of band gap. So there will be such opening. It means that spin waves with this k in the frequency range, in this frequency range, will be reflected. So for them, it acts as a crystal, as a mirror. But as soon as you go to larger k, so smaller wavelengths or smaller k, larger wavelengths, it works as a mirror, like it's shown here. Third way to look on the same would be in terms of momentum conservation. So you see the distance between these two k is 2 pi over a. So you have here pi over a and here pi over a. And that's what really happens in your system. If you want to work in reciprocal space, you can say that this lattice simply induces additional momentum to your system, which is 2 pi over a. Yeah, and if you discussed Bloch theory of free electrons in crystal, then principally it solves the same physics. Good. If you work with photonic crystals, then most likely you modulate and you want to create photonic crystal, yeah, in photonics, you will modulate refractive index, simply silicon oxide, and then you make holes, and the refractive index of air will be different than in silicon oxide, and so on. In this sense, magnonic crystals have advantages, because in the simplest formula, which we have used before when we discussed magnetostatic surface spin magnetostatic waves, I think this backward volume, and here additional taking into account this quantization over the width, so here's width, and you have here many parameters: applied magnetic field, magnetization, width of your waveguide, and thickness of your waveguide. And principally, we have shown that you can modulate all these parameters in order to get magnonic crystals. So, and that's some of them we will discuss today. So you can change field periodically, you can change saturation, magnetization, can change width, or you can change thickness. And all of them works as a good magnonic crystals, and you have many advantages how you can do it. Yeah, and let's start with the most classical one. It's a group-based magnonic crystal. Again, here, this transmission curve we already understood. That's how transmission looks like, and that's how it looks for the case without grooves. But if you will etch grooves on the surface, you will see appearance of such band gaps. So here we have 1, 2, 3, 4 band gaps. As a fun point that this is probably the first magnonic crystal, and it was published 20, 30 years before term magnonic crystal was born, so a long time before. People just were thinking how to make micro-resonator. Cycus, I think, was, I don't have the very, but here we refer, this is our first paper, so we kind of recovered this direction. What we did first, the first time, we were the first who studied how it works in the backward volume geometry, but in there you will find references when people studied the same structures in Diamond-Ashbach geometry and forward volume, which were more attractive for micro applications. And yeah, so this all was done in the frames of project written by Alexander Serhai in Kaiserslautern, and I was postdoc in this project. And but coming back to this one, we see this formation of band gaps, and principally everything what I said to you is clearly visible. You see big reflection here and here. So this is really a big reflection. You have from 35 dB to 55 dB. So it's like 20 times larger. It's 20 dB, so it's 100 times stronger reflection between this and these points. But you still see some parasitic reflection in between band gaps. Yeah, so still you change the transmission of the of your waves through the structure in between band gaps, but with only weakly. Then you have this groove 300 nanometer thick waveguides, and how they were produced simply using orthophosphoric acid etching. So it's a very fun story. The TIC, it's a material which very hard to, it's very hard in mechanically but also chemically. There are not so many acids which you can use to etch them, and the acid which is used to etching is orthophosphoric acid. And this is a very fun acid because, to the best of my knowledge, we drink it every day with Coca-Cola, but when you will heat it up to 100-something degrees, it's getting quite crazy. And the only acid which I know which eats yttrium garnet. Therefore, what was done, we had this structure. We placed mask. We can use silicon oxide, but then it doesn't work good. So we developed some another technology in Kaiserslautern, simply organic photoresist, which was baked properly that it's getting stable against the acid. We etched to 300 nanometers measured transmission. And we see band gaps. And we etched it with a step of 100 nanometers and measured again. So I was running between clean room and the lab. But for 600 nanometer, you see that it's getting much deeper. So the larger the depth of the grooves, the deeper is this band gap and brighter it is, and also parasitic losses are increasing. So you see the stronger reflection efficiency, that what happens is width actually is defined by the reflection efficiency. And if you have 1 micron, which is around 20% only of the thickness of the waveguide, we have seen no transmission anymore, so more or less EEC was killed. Good, so that's so much about magnonic crystal. And yeah, if you will plot rejection band loss as a groove depth, you will see such points that we could rejection band only for the first band, yeah, which is the smallest, because second, third rejection efficiency was much efficient. But even here we could reach 30 dB, which is 1,000 times, which is quite cool. And here you also see this solid line. It's a theory. I will come to it. But if you will go to rejection width, also it changes. With the increase in groove depth, it increases. And then it goes to 30 megahertz in this case. And there's also theory which shows qualitatively trend properly, but quantitatively doesn't agree. What is the theory? It was developed under the supervision of Mikhail Kostelov, who is now in the University of Western Australia, and he proposed, let's do the following. So we had a lecture about microwave business, and we know that if you have microstrip line and you have different characteristic impedance at 0, Z, at 0, Z, then there will be reflection as a change in characteristic impedance in some, and it's defined as Z minus Z0, Z plus Z0, like it's shown here. And what Mikhail proposed, he said, let us actually try to introduce some efficient characteristic impedance for spin waves, and then if you use approximation of linear dispersion curve and so on, you could show, so we did it in this paper, you could show that principally it will be, I think, inversely proportional to K of your magnon. And then what we did, we said this is our magnonic crystal, let's make simplest possible finger-like model, and we will then expect reflection from each side of this side of the group, this side of the group, which is given K minus K0, K plus K0, so more or less this formula. And we also can rewrite it for the case of linear dispersion in the way that here's delta, it's a group depth, and here's 2D0 minus delta. Besides, you see there is this parameter eta, which is more or less nothing else as fitting parameter, because model is so simple, and in physical experiment we can expect many other experimental findings, and therefore we just plug this parameter to tune experimental theory, and then after we match them, we have some value of eta, and we can start thinking what is it, if it's larger than 1 or smaller than 1, and what can contribute to it. So after you define this reflection from this region, then we again coming back to microwave technique. There was this T parameter. So there are S parameters which we use every day in the measurements, but there are T parameters which are defined differently, slightly differently, but idea is the same. And why it's important? Because you can then now define 4 T parameters for this reflection. For transmission, here spin wave propagates. It means that this matrix will be defined simply as a phase accumulation over the distance A minus WG with damping. So here K0 2 prime, which means damping. So this describes phase accumulation of the wave. T3 matrix here defines your phase accumulation in this small region, but with different factor, because your K is different in the narrow inner waveguide. And at the edges between these regions, T2 and T4, it's given simply by the reflection, by this gamma parameter which you defined. And why it's interesting, because then what you do, you just multiply all these matrices, and that means that you have transmission T matrix for one period, and then you put it to the power of number of periods, and you will get more or less the simplest model to describe T parameters of your magnonic crystals. And you see, with principally we see quite good agreement, but there was one fitting parameter, this eta. And when we actually, then what we did also, we decided to change, to check how this magnonic crystal behaves for backward volume and for magnetostatic surface spin waves. And we see that for backward volume it behaves like this, and for MSS wave it behaves like this. And then you see that it's very different, yeah? For example, for half micron groove depth, backward volume already practically doesn't propagate, and for magnetostatic surface waves will have only weak gaps. This was of course confusing and interesting. And if you speak about this eta parameter, so here it's smaller than 1 and here it's larger than 1. So it means that backward volume are scattered larger than it's expected theoretically, and Damon-Eschbach smaller than it's expected theoretically. And what are the reasons? So here actually I don't want to go into all the details, but principally one, we were thinking that maybe backward volume, Damon-Eschbach is scattered back because of this localization, but it's hardly probable because it's 95% only, so here's 100%, here 95, so it's practically uniform was our key. We were thinking that, this excitation of antenna is non-reciprocal, maybe groove also works in the same way, the scattering mechanism, but also hardly, because it's a different physics compared to when you send microwave signal. So therefore, most likely the main reason is that in backward volume magnetostatic wave, each of this groove, when you have scattered, excited this first mode, it will generate all higher order thickness modes pretty often, which are not propagating. So probably this very pronounced band gaps for backward volume waves are associated simply by the excitation of higher tending thickness modes under the grooves. Good. Other question?
I wanted to ask about it from the signal we saw before for the magnetic crystal. If we can go back.
This one or more?
Yeah, here, for example. There was this slight increase of the signal at the end, in the FMR. Is that because of the higher thickness modes?
So Fabian is asking if we have this little increase in signal here due to the higher thickness mode. Honestly, I don't know. I can't answer. I never paid attention to it. Maybe it's just some artifact of experiment. So I would have to check first of all if it's systematic or not, and then to start thinking. But maybe you're right. Maybe it's not necessary. Oh, sorry.
Yeah.
Yeah, it looks like there is something. Yeah, maybe it is, but I don't think it is a thickness, but width mode, because this chemical action, and so on, we probably. It might be that sample became not so symmetric, for example, because if sample is asymmetric, it's, I don't know, you damaged one side of it. Then this higher width mode should be possible to excite better, I think. And maybe this is a signature of this one. But yeah, I cannot answer confidently because I need to investigate. Yeah, thank you for this question. Good. Okay, guys, so we discussed thickness. Let's quickly run through other types. This one was also one of the first papers in the field about width modulated magnonic crystal, but it all was numerically simulated at the nanoscale. So you see sizes like 10 nanometer, 15 nanometer, which is cool. It means that magnonic crystal can go to the CMOS sizes, but very hard to realize. And then we see the stop bands here shown like this. So it's all good. For us, of course, experimentally, the question was if it's possible to bring it to the microwaves to experiment. And this is our first experiment in Kaiserslautern. We had used permalloy, 2.5 micron wide, 1 micron periodicity, and these notches are like 25 micron large and, I don't know, something like half micron in depth. And then we used microstrip antenna, simply strip line antenna, to excite spin wave in the reference permalloy waveguide without notches and the waveguide with the notches. And principally, if it's a condition for reference waveguide, here we work with the Eschbach mode, so you see dispersion goes up. Here it goes like this. Then what we do not have second antenna. Here brilliant light scattering was used. So we just focus the beam 8 micron away from our waveguide. And we see that when you measure the same for magnonic crystal, you see such a band gap here, formation of band gap. So it was a proof that this width-based magnonic crystal works good also at the nanoscale. In reality, in theory, I agreed. It was shown that you can change this band gap frequency simply by the change of applied magnetic field, which is also advantage of magnonic crystal. Principally, everything works well. The only what you need to keep in mind that here in reality we have excited several width modes. So here we clearly have seen presence of many width modes, and this band gap in reality is accumulation of several width modes. Moreover, this width mode have different dispersions in this region and in this region, yeah, because width is different. So it's a bit more complicated. Crystal, unless we go to single mode regime, like nowadays it's possible, like 300 nanometer wide as a waveguide, principally we would suffer from multi-mode behavior. Good. Dynamic magnonic crystal. So very interesting topic, because it's another type of magnonic crystal. Imagine that you have a spin wave packet which propagates in your media, and then you instantly change properties. That it's, for example, is forbidden in this media to have this frequency and this k. And then it's a question: what happens if you create such situations that media instantly is not anymore eigenstate of this packet, and then you will get access to new physics. In optics, people are interested, but it's very hard to realize because light is very fast, and you need to change media faster than light is changing. In spin waves, it's easier. And such crystal where you change properties faster than the lifetime and faster than propagation. So this is your input antenna, output antenna. And you can change media, switch on or off this magnonic crystal, like it's shown here, faster than spin wave runs through. This we named dynamic magnonic crystal. Yeah? So it's opposite to reconfigurable. Reconfigurable means that you can change properties slowly. Dynamic means that you need to change it very fast, and then you will get access to new physics. So we have this meander strip, and it was done on aluminum nitride that you can get heat sink, very good. Aluminum nitride is a good heat sink. You send DC current, and when you DC current, you see that it changes polarity here. Then you will modulate your field like it's shown here, and for half ampere current, you can modulate plus minus 5 ampere Ørsted on the top of 1600 Ørsteds like this. So there were 20 periods. Periodicity was 300 microns, so it was macroscopic sample. The problem, what happens if you will put such a microstrip line on top of your YIG surface, you will see such that your transmission curve is getting very bad, because each of these wires will work as an input antenna and will re-emit something, and next one will, so it will excite this one electromagnetically, this one will emit, so you have here complete mess, and that's exactly what we see. The solution was actually proposed to me in private discussion by Boris Kalinikos. He said you need to put a spacing in between. And what's going on here, because when you put spacing, the field created by antenna decreases 1 over r distance, but field, which is quite slow dependence, but field created by YIG, by spin waves here decreasing exponentially as in one instance wave. So it means that this dependence from YIG is exponential and fast, and this one is slow. Therefore, you can, by increasing spacing, you can get such a point that these antennas do not feel any more field created by antenna, by YIG, but YIG feels field created by the wires. That's exactly what was done. Then, of course, you need to pay price. You need to increase current to half ampere, like it's shown here. But it works good because you see that with a spacing of 50 micron, if I remember right, just piece of glass, we see again nice transmission curve. And then what we do, we just send DC current through it, quarter of ampere, and you see formation of such a band gap. Half ampere, you see band gap became wider, also deeper, but here you don't see it because of electromagnetic leakage. And principally, you could tune band gap width by the applied current. Also pay attention that we have only one band gap, second one practically not shown. Andrii, what is the reason for that we don't see band gap? In the previous course, we have seen many band gaps when there was such a rectangular profile. And here we have sinusoidal profile of magnetic field, and we see only one band gap, and second is not pronounced. Why? No idea, Rusty?
I think the Fourier transformation of this.
Yeah.
Delta function.
Correct. Yeah, you hear exactly, you need to take a Fourier transformation. Exactly like when we discussed antenna. You have, if you take such a rectangular profile, when you take Fourier transformation, you will have many delta functions. And if you have one sinusoid, you take Fourier transformation, there will be only one delta function. That's exactly what we have seen in this experiment. Good. So here shown for 3 different currents applied, how it behaves. Rejection means depends on applied current. Everything is quite straightforward. And now we are coming to interest in physics. So I said that very interesting experiment will be what happens if media changes faster than the spin wave propagates. And we can perform such experiments that we apply spin wave amplitude, so it means that there was, so that's actually, we tested first of all how fast we can change. So there was, we measured just continuously spin wave outcome at the output antenna, so constantly sending current to the input and see what's going on at the output, and then at 0 nanosecond we switch on this magnonic crystal. And you see that then it takes around 70 nanoseconds because spin waves were already here and we switch on, still something has to propagate from this point to the end, and it took 70 nanoseconds. And then there was no spin wave transmission, so practically 0, so we closed crystal. And then we opened it again, so here current is switched off. And it doesn't propagate. And then what's going on is it still takes 270 nanoseconds, so the spin wave from this point will reach output again, and again you see signal. So we have tested how fast we can switch it on and off for the 10 nanoseconds, principally very fast. And transmission time between antennas is 300 nanoseconds. Good. Now, so this interest in physics, principally we are going here shoulder to shoulder with photonics people, because they were thinking how to do wavelength conversion, for example, by dynamically reconfiguring a photonic crystal cavity. Some people tried to do stopping and time reversal of light. Some people tried to do reversals, time reversal, so-called phenomena, and without nonlinear multi-photon effect. So there is such phenomena as wavefront reversal, time reversal, when you make phase conjugation of your pulse. It's known in optics, but it's always relied on multi-particle scattering, multi-photon in this case. And people already at the time were starting to search how to replace nonlinearity with non-stationarity, to use dynamic crystals to replace nonlinearity completely. And that's what we also have shown here. So let me explain you how experiment was performed. Quite easy and interesting. So our 2 dispersion curves, so backward volume running in one direction, another direction, assumption of linear dispersion curve, magnonic crystal here. We sent pulse, and at some moment, we froze in time, all our pulses sitting within magnonic crystal, and we know it, describe it as excitation of large intensity of spin wave. So this big circle means a lot of energy sitting in this mode. In this moment, we send a pulse to dynamic magnonic crystal, we excite it, and it starts to move, wants to move back. It means in terms of dispersion curves that energy from this mode is pumped to this mode. It tries to propagate to backward. But the problem is that for this one, there is also back grating. So it cannot run in one direction, it cannot run in another direction. And it just jumps back and forth. So energy, more or less, while staying here, it's trying to move to another, one or other direction. It oscillates between these 2 curves. The physics here is very simple. It's just two couple oscillators which pump energy from one mode to another. So you see now all energy is in red, nothing in blue, but after some time all energy will be in blue and nothing in red. And that's exactly what happens in this case. Energy is pumped from one to another and back and forth. And that's exactly what we have shown. Experiment was demonstrated very easy. You switch on crystal when pulse is in, but you release it in different times. So you just couple and duration you change. And then you see that there are really oscillations when all energy goes to the reflected power back to input antenna. Then after some period, it all goes to that antenna, then back. So if you normalize one to another, principally you see these reflections. Or if you would do it in quantum world, you would name all these Rabi oscillations. And yeah, so there was small phase shift. We still don't know where it comes from, but probably from some experimental peculiarities. But important is that we clearly have shown that we can couple these two waves together. We can further it here. Now let us tune such a duration of the pulse, 20 nanoseconds, which is optimal to reflect pulse back. So it means that this pulse will be reflected, and then let us change the frequency of this pulse. At this point, it's very important for understanding of spin wave physics. So Andrii asked me in the BLS lecture if BLS can be explained by Doppler effect and Bragg. This is a very nice demonstrator that all these phenomena are about energy and momentum conservation. So you need to keep in mind always where you need to take it. Imagine that now we changed the frequency, but we are still staying within the band gap. And we apply this very short pulse, 20 nanoseconds. What happens in this case is that we induce in the system momentum 2 pi over A. And this momentum is fixed because we have magnonic crystal, we have period, and it means that we cannot change momentum somewhere else. It should go here only. But if it should go here, you see that at this frequency there is no wave. It's not allowed. And then system is thinking, okay, what to do? I need to conserve energy and momentum is already given. Can I change energy? And the answer in this case, yes, because you have this very short time. So you change something in your system very quickly, and that means that in the frequency space 1 over 20 seconds, you should be able to change frequency of your spectrum, of your wave. Therefore, what happens here, it changes to this frequency. So it means that you have a reflection with a change in frequency, and not simply change, but with inversion of frequency. So it means it's inverted with respect to this line. If you go to smaller frequency, this one will be higher. And that's exactly what we expected from this idea from Vasil Timurkevich, and I was lucky to test it. And really, that's exactly what we have shown, that middle of frequency 6.5 gigahertz, it's a middle of band gap, and then when you increase the signal frequency, the reflected frequency decreases. So it means that we've got a frequency conversion. Yeah, and if you would apply such a complex pulse, then your reflected pulse would be inverted. Very interesting phenomenon and purely linear, because usually you need nonlinear phase conjugation for this. And the same phenomena brings you to all linear time reversal. Time reversal, it means the following. So if you have input signal, AS of time, you can show it in form of such a series. And reflected signal, what happens here, delta F, yeah? And this frequency conversion means a change in delta F. But instead of changing delta F, you can change also time. Yeah, so it doesn't matter if you change sign here or you change sign here, time. Important is that this sign will change. So it means that when you do frequency conversion, it would be the same as time inversion or time reversal. It means that your pulse is inverted in time. And how to show it? It was shown like this. 2 pulses were applied, and where then you measure, this is applied 1 pulse, another pulse, and then you measure transmitted pulses. And then you start to switch off. You switch off first one switched off, second is still here, staying here. You see that you excited second and you detected it transmitted. Yeah? If you do switch off another pulse, so you kind of can say which pulse corresponds to what. Now what we did the same with the time reversal. So we sent 2 pulses, we apply this 20 nanosecond pulse to dynamic magnonic crystal, and both pulses are reflected. And then 2 input pulses and 2 reflected. And when you switch off the first one, second disappears. when you switch off the second one, first disappears. So it means that this pair of pulses is inverted in time. So this is 1, 2, 1, 2, and here 1, 2, 2, 1. Yeah, and this is very easy to understand simply with this animation. So standard reflection, which you have like from mirror, looks like this. Yeah, so first we had short pulse and then long pulse, and it inverts. Now, and then excited and detected pulse, if you plot it in the terms of time, you started to excite short pulse, but also when it comes back, you start to detect short pulse. That's why it's symmetric. It's a standard picture. What happens if you have a train, analog of train? It behaves like this, yeah? It's just standard reflection from mirrors. That's what we see every day in mirror. What is time reversal? Time reversal is nothing else than this behavior. You just start sending it back. And now you detect first big pulse and then you detect small pulse. This is excited, this is detected, and time profile of this pulse is inverted. Yeah, so it means something like that. Oops. Sorry. Yeah. Teleportation with multiplication. Yeah, so some bug in animation. Good, so that's what we have. It's just time reversal. Why it's interesting for analog data processing? Theoretically, it can be. For example, you have some audio recording, long one, and then if you want to play it backwards, you would need to do a lot of processing in your processor. But if you will have some analog signals, then principally with one operation you could turn it. Of course, in reality, for spin waves, it doesn't work because they are very fast and very high frequency. But somehow in the processing with phase front, it's of interest. Good. So much about this one. And very last part of magnonic crystal, again, just to show you another experience. So now we just have seen how system behaves if you have dynamic system. Yeah, how you deal with energy and momentum conservation when you have something changing very fast in the system. Now let us look what happens if you have something moving in the system. And this one we named traveling magnonic crystal. So the idea is very simple. We have only one antenna. Oh, okay, second also can be. We excite spin waves, and from this side we excite surface acoustic wave. They interact, so surface acoustic wave works as a scatterer for in spin wave, and it propagates backwards. Yeah, and here what we investigated, we worked with backward volume wave, and as we know already, backward volume magnetic wave, backward volume magnetic wave propagates in one direction but carries energy in another direction, so it has negative group velocity. And why it's interesting? Because usual Doppler shift frequency of the reflected wave from this plane will be increased. So here frequency should be higher than this one. But in the case of, but in this case, we have the opposite situation, that if you have wave with negative group velocity, frequency of the reflected wave will be decreased, like it's shown here. How the experiment was performed? Quite quickly, 2 spin waves that we can measure transmission one other direction. And here was placed piezo, which excites bulk acoustic wave into this wedge, plastic wedge. And then by tuning this angle properly, you can convert this bulk wave here into acoustic wave, which propagates in YIG GGG. For acoustic wave, YIG and GGG have the same properties. Therefore, wave runs over the whole stack. And here we have some damper to absorb acoustic waves, and also some cut edge to absorb spin waves. What is the problem now? Again, coming back to this point, energy and momentum. So now the story is somehow similar to that what we discussed in brilliant light scattering. We have magnon excited here, and here is transmission line, so we can scan along this. For all frequencies, we change K. And here's our acoustic wave. It has 10 megahertz frequency, very small frequency, and comparable K. And now somehow we need to find such point where we can satisfy energy and momentum. And you see, energy and momentum for acoustic wave is given. It's simply given by your piezo. It means that you need to find now such a scattering of this magnon to another magnon when this k will be conserved. So it means that you need this delta over k should be given. So you need something with this k, and you need something which is 10 megahertz detuned, up or down, something 10 megahertz. So it means that you are searching for magnon when it happens, which can be here. And if you use VNA, and principally you see nothing here. This process is not possible because you don't have dispersion curve. And there is nothing dynamic that you can shift it, except this given velocity. But then when you scan it, at some point, you will find such point that you can satisfy energy and you can satisfy momentum. And when you measure an experiment, you see that really there will be some scattering. So it means that with vector network analyzer, you could check all waves and have found only one point when energy and momentum are satisfied. And by the way, it's very interesting that VNA, modern VNA allows you this possibility to measure at the frequency different from the applied signal. So you apply 7 gigahertz, but you measure at 6.990. With shifted frequency, because here it was important to measure a different frequency because of the Doppler shift. And principally, it's very nice that another example how you work with traveling, with moving objects. And in this case, again, not velocity was important principally, if to speak about energy conservation, but important was frequency of surface acoustic wave. Like in brilliant light scattering, important is not speed with which magnon is moving, but as a frequency of magnon, because it gives you energy. And that's the nice example how we could see the interaction of surface acoustic wave with spin waves, although the interaction itself is very weak. YIC has very small magnetostriction phenomena. And this was the last slide for this lecture. Other questions or comments? It's not the case. Russell?
Yes, in the experiment you've shown for the picture on the right, you said you excited at 7 gigahertz. So,
approximately.
I understand then the certain acoustic wave is the difference.
Yeah, it's the difference between these two frequencies, so it's
So it's only an example with this 10 megahertz, and in the experiment it was like 500 megahertz. So,
no, it's an experiment, it was 10 megahertz, but here it was not 7, it was 6.55. Yeah, but it's really, you are searching for two waves with a difference in 10 megahertz frequency, but also K is very important. That's why it was cool system that we could have, that acoustic wave has comparable distance as spin wave, comparable wavelength, sorry. Good. Okay, I see no more questions. Thank you for your attention.